Let's dive into it. So here what we're doing is we are following, let's see, these four things. Okay, draw free body diagram, assign coordinate frame, compute reaction forces, moments, and then finally the fourth part, which is actually the lengthiest part, compute the shear force and bending moment diagram. The people who are behind, can you hear me loud enough? Okay, so I don't need an extra microphone. I don't know how effective this is. Is it different now? Okay, now it's better. So it's now it's working. Okay. Okay, so let's get started. Let's first draw the free body diagram and compute the reaction forces. Okay, so the left side we had a hinge joint. So let's put two reaction forces there, one in the horizontal, one in the vertical direction. And then at a 0.8 meters from the left, there was a roller. So I need to put a vertical reaction force. And on the right side, there is a force of 20 kilonewton. And then there is a bending moment of 150 kilonewton meters on the right. These lengths are 8 and 3. Okay, so that's my free body diagram. You can assign the coordinate frame, which is pretty much standard. Horizontal is along the X, vertical is along the Y. Okay, third step, compute the reaction forces using equations of equilibrium, which is summation of forces in the X direction equals, in this case, HA, which is clearly 0. Summation of forces in the Y direction equals VA plus VB, both are in the upward direction, so that's positive. And then we have 20 kilonewtons acting in the downward direction. And then there is a 40 kilonewton per meter force. So now we need to convert that force per unit length into a force. And so you can see that's divided by the length. So I need to multiply it by the length about which it acts. So it acts over a distance of 8 meters. So 8. I think that's about it, equals 0. Okay, so this will give me one equation. It's 340, I think. 340. Okay, I need another equation to solve for PA and PB. That would be the moment equation. I can take moments about any point I choose to. Let's just take it about A. So the moment about A equals 0. So let's write that. Let's take the easier ones first. VB is easy, right? So VB acts at a distance of 8 meters from A. So VB times 8. Now the direction of that is going to be counterclockwise. So I put a positive sign. Then we have the 20 kilonewton force. It's acting at a distance of 11 meters from A. And then if you see the way it's positioned, it's going to create a clockwise torque or moment about point A. So negative. The 150 kilonewton meter force, moment is in the clockwise direction as it's shown here. So it's simply 150. And the last one I need to write is the moment due to the 41. Now, the way this works is, assuming this load is uniformly distributed, you can assume that the net force, in this case, the net force is 40 times 8, right, is 320, acts at the midpoint about which that force is acting. In this case, what it means is, for all practical purposes, for finding the moments, we will assume it's a concentrated load of 8 times 40, which is 320, acting at 4 meters from the left, which is half of 8 meters. Okay, so now it's kind of easy to write the equation, because we've reduced that from a distributed force to a concentrated force. So that's going to be 320. That's the force at a distance of 4 meters from the left. So 4. And then since it's acting downwards, the moment about A is clockwise direction, so negative sign. All that equals 0. Okay, so I did the math earlier. So the force VB comes out to be, I got it, 206.25 kilonewton. And then subbing that in, sub in 1, which is right here, you can find what VA is. VA is 340 minus 206.25. So VA is 133.75 kilonewtons. Okay, let me know if you have any questions. Okay, so now we've got the reaction forces. The fourth step is the most tedious one, which is to draw the shear force and bending moment diagram. So let's do that. Let's just divide the page into 2. Okay, so x equals 8, b equals 186.25, which means that the shear force here is negative, minus 186.25. And so you can see that the equation for V here is a function of x, which means it's a straight line. So if I have 2 points, I can join those 2 points using a straight line. So I just join those 2 points. And then sometimes it's of interest, what exactly is this point, right? You want to know where exactly this point crosses the x-axis. It's actually quite simple to do that. All you need to do is you have to put V equals 0, right? Because the shear force there is 0. And then solve for x. So if you solve for x, which is 133.75 divided by 40. It's 3.43. Okay, so that completes this equation. Now, next equation is this one. which is valid from x equals 8 all the way to 11. And we see that that force is simply 20. So I just need to draw force at 20. And then eventually, when you reach here at C, you'll see that there's a force acting downwards. So the net force at C is 0. So the curve looks like this for the shear force. Okay, so here's how you would do it when there is a distributed load. Now let's solve for the moment. Okay, so we do the same thing, which is we start cutting the beam at points where the force or whenever there's a force or moment, we just cut those parts, and then we write the force moment equilibrium equations and then solve for the moment. So let's do that. So first we go from A to B, cut it between the two. On the left side, we have 133.75. On the right side, we have V. That's 40 kilonewton per meter. And then our convention is counterclockwise movements on the left side of the beam are positive. So that kind of completes what I need in the diagram in order to solve for this. So now let's write the equation of moment equilibrium. That would be, I would take moments about this point. Okay, now if you don't want to do that, you can take moments about A, that's fine too. I'm taking moments about this point because I really don't want B to appear in the equations. But if you want to take moment about this point, you'll have to put the value for B based on the shear force diagram and then solve for the moment in, which is absolutely fine, I'll give you the same answer. If you take the moment about that point, you would have 133.75 acting at a distance of x from the point at which I take the moment. And you can see that would induce a clockwise movement. Since clockwise is negative, right? This is positive, counterclockwise. I would put a negative sign. Okay, so then there's M, which is counterclockwise, positive. And then I need to find the moment due to this distributed load. Now, what you can do is you can do the same thing which we did for the reaction forces. We can assume that that force acts at a point which is midway on that section. So in this case, the force would be acting here, right midway on that part of the beam we've considered. So it's going to be at a distance of x divided by 2 from the left, also x divided by 2 from the right. The value of this force is going to be 40 times x. Okay, so the moment is going to be 40 times x, that's the force. As I said, the distance of the force 40x is x divided by 2 from the right side. So I would have x divided by 2. And then for the sign, about this point, about which I take the moment, is going to induce, this force is going to induce a counterclockwise movement. So the sign is positive. Okay, so let's simplify this equation. It comes out to be minus 20x squared minus or rather plus 133.75x. So we've so far never looked at a moment equation which looks like a quadratic, but this is a quadratic equation. So it's not longer a straight line. It's going to be a curve. We will come to that when we draw the bending moment diagram. Okay, so that's that for A to B. Let's go from that to B to C. It's the same diagram as the left, except that you put a moment and to analyze it. Okay, so we do the same thing. So we take moments about the cut. So let's, okay, so M is counterclockwise, so positive. 133.75 acts at a distance of x, as you can see. So it's going to induce clockwise movement. So I put a negative sign. The 206.25 kilonewton force acts at a distance of, so since this is 8, the distance at which it acts is going to be x minus 8, right? X minus 8. And then the sign on that would be, since this force is upward, it's going to create a clockwise torque, so a clockwise movement, negative. And then the 40 kilonewton per meter force acts in x in its entirety. So the force due to that is going to be 40 times 8, 320. And that force will act midway of this part of the beam. So it's going to act at 4 meters from the left. So that's going to be 320. And so we just have to figure out the moment arm, which is a distance of, this part is 4. Right, so it's going to be x minus 4 on the left. So 320 times x minus 4. And you can see that it's acting downwards. So about this point, it's going to create a counterclockwise torque. So positive. All this equal to 0. So I can simplify the equation for M. It's actually pretty simple here. M equals 20x minus 370. So you can see that the equation is linear in x. So that's going to be a straight line when we draw the bending moment diagram. Question?
Starts off and starts to go down. Right, so like would you just do half of that?
So he's talking about this. What if the force is okay? So it's like a triangle, in which case, so let's say that this is W kilonewton per meter, but it's not quite rectangular. So in this case, if you want to find the effect of this force, it's actually, what you need to know is that where's the centroid of a triangle? I think it's 2/3 from here, so it's 1/3. So if this is L, then act. So this force is going to be, all you need to do is find the area of a triangle. So in this case, this is W, that's L. And so the area of a triangle is half W times L. So that's the force. And this is the momentum. And so you just use this logic when you have cuts. But yeah, that's a good question. I'm trying to avoid giving you such questions because I think that that's not the point. The point is to actually go to stress. So it's good to know that, but I won't really test you on this. So don't worry too much about it. Okay, so we have this. Let's just draw a bending moment diagram. Okay, so all we need to do is look at those two equations. So first we have this equation. Over here between x, 0 and 8. And then we have this equation, which is from 8 all the way to 11. So let's put x equals 0 here in this equation. So if you put x equals 0, you see that the moment is 0. So it starts off with 0. And then at B, we would have x equals 8. So at B, x equals 8, m equals minus 28 square plus 133.75 times 8. That comes out to be minus 210. Okay, so we have this point, and then the question is, how do you connect the two? Right, so this is where it's helpful to have a graphing calculator, which is by the way allowed. And if you actually plot this as a function of x, you will see that it looks something like this. Okay. So if you don't have a graphing calculator, then you need to actually put in the values for x at different points. That's one way to do it. Another way to do it is, if it's a quadratic, the question is, would it be, so we know it's going to be a curve which would have something like this. So the question is, would it be upwards or would it be downwards? And what you need to do there is in calculus, you can find the maximum minimum of the function. In this case, it achieves a maximum at a certain point. It's that point is 6.6875. Okay. And the maximum there is 223 point. So I think it's too many things to do if you think of maximum minimum. Some people are not comfortable with that. In which case, I would just recommend that use a graphing calculator, put in the equation from x equals 0 all the way to 8. It'll give you those points and just plot that. Okay, so that's the curve there from x equals 0 to 8. You need to use this equation for the part from B to C. So we put x equals 8. It'll actually come out to be the same as I've drawn here. Then I put x equals 11. If I put x equals 11, you should get, so 11 times 20 is 220 minus 370, that's minus 150. And then how do you connect the two? Well, you look at the equation. In this case, the equation is an equation of a straight line. So I just draw a straight line between the two. So that is the, let's say, fairly complicated bending moment diagram. That's how